Okay, so actually through K1ZZ and they the HamSCI organization reached out and indicated that they have some programs together to popularize, inform everyone of the upcoming solar eclipse, April 8th. Here in the Northeast, we are under the path of totality. I'll be in Danville, Vermont that day. And be deploying a field day style station with 80 to 10 meter capability. Um, and so what we do is brought in, so HamSCI has a number of members that are basically ambassadors to try to drum up some support from this. Gary Mikitin, AF8A, if you check your logs, I think you'll find him in there. Frequent contester. And as I said, as I mentioned, he's a coordinator for the HamSCI's Solar Eclipse QSO party and Gladstone Signal Spotting Challenge. With that, Gary, why don't you take it away? I'll stop the share here if you want to share your screen.
Good. Thank you very much. Yes. How's the audio sound?
So the audio sounds good.
Okay. I'm going to hit share screen, and I'm going to try to remember to also share my audio because I do have one clip that's part of the presentation. Share sound. I'm going to check that, and hopefully that'll work when we get there.
Okay.
Okay. Get some of this Zoom stuff out of my way. The play button. Okay. Hopefully you guys will see it nicely and clearly, my opening slide.
We
All
do.
right. So good morning, everyone. Thank you very much for having me here and speaking on behalf of HamSCI. I guess I'd like to say greetings from the Black Hole in Cleveland, Ohio, a couple of hops further away from Europe than most of you are. Like many of you, I'm a longtime ham. I'm closing in on QCWA times 2. Not quite there, but getting close. Professionally, I'm a retired electrical engineering. I went to college here in Cleveland at Case Western Reserve, and it's hard to believe it's going to be 40 years since I graduated. It kind of shocks me every time I say that. My role today is as a citizen scientist. It's a fancy term for a volunteer for HamSCI. I'm not one of HamSCI's scientists or researchers by any means. And what I do know, and I'll talk about a little bit about geophysics and heliophysics today, it's mostly all I've learned from other HamSCI members. Today, I hope to explain a little bit about what HamSCI is all about, how data generated by HAMS is helping us better understand our physical world, specifically the ionosphere, and how everyone here can contribute, I think, both to your enjoyment, because it's another contest or two, and also to our understanding of the world around us. So let's see, there we go. So yeah, I gave a few of my particulars, a couple interesting photos. I think many of you probably know Goose, W8AV on the left. He and I were getting ready for an Ohio QSO party. In the center is Jim, K8MR. He and I were probably heading out to Pennsylvania. And on the right is myself operating at WWV in Fort Collins, Colorado. That was the 100th anniversary of WWV going on the air. And WWV plays a big role in what we do, and I'll get to that in a second. I do want to acknowledge that the presentation I'm doing today was originally created by Dr. Nathaniel Fursell. He is the guy who started HamSCI in 2016 and is still leading our efforts and does a tremendous amount of work as a professor at the University of Scranton, as a member of his local clubs, a member of FRC, and so on and so forth. So most of the material you've seen here is a lot of it is due to his hard work. All right, so what is HamSCI? We call ourselves a collective. We're a volunteer organization. We're not a nonprofit. We're not a corporation or any of that sort of stuff. It's just a lot of people who are interested in space physics, space science, how the ionosphere works, and how we can better understand it. HamSCI has 3 main goals: advancing scientific research through amateur radio activities. That's really important. How many other scientific research efforts involve HAMS directly? We work very hard at developing new equipment. We use HAMS, our knowledge and our experience extensively in designing equipment to study the ionosphere, and also, of course, providing educational opportunities. So people that may not have ever been exposed to any of these concepts in the past can learn and then contribute. Okay, so as I said, our main area of focus is the ionosphere. And I think everybody here is probably familiar with the ionosphere and its different layers. This is a nice graphic that was pulled off of Wikimedia. But as a quick review, we're talking about mostly about HF propagation between 3 and 30 megahertz primarily. Well, 160 as well, so maybe I need to drop that lower number. The ionosphere, of course, is an electrically charged region of the upper atmosphere. It starts around 70 or 80 kilometers above our head, and it can extend 5, 6, maybe even 800 kilometers overhead in an altitude. It's created primarily by ultraviolet and X-ray radiation from the sun, stripping electrons off the neutral atmospheric particles, thereby producing an electrically charged gas known as a plasma. Thankfully for us, that plasma refracts HF signals, and I've got some interesting diagrams. Of course, during the day, we've got multiple layers, F1, F2, E, and D. At night, when the sun's no longer shining in the atmosphere, those layers recombine. And that day-night transition is particularly interesting. I think most of you are also familiar with gray line propagation, and that's one of our areas of study. So, unless you've been living under a rock, or I don't know, maybe on Spratly Island or something like that, you know that there's an eclipse that just happened in October and another one that's coming in April. And these provide some very unique opportunities to do scientific research. So that's why we're promoting our Solar Eclipse QSO party and some other events. Be aware also that we don't have a total solar eclipse going across North America for about another 20 years. So that's why we want to make hay now and learn as much as we can. So as I said, HamSCI's near-term focus is the eclipse that's coming in a couple of months. And we did collect a lot of data back in October during the annular eclipse. So our SDQP had a bit of a challenge, our contest, because it happened on the exact same day as the PA, Arizona, and Nevada QSO parties. But more people on the air was a good thing, and I'll explain how that works. So I'm going to show a little diagram here. This was, of course, last October's eclipse, a little graphic of the eclipse path, which I think you'll find interesting. So I traversed the western and southern part of the U.S. and then through Central America and across Brazil. So I'll let this play again, then I'm going to stop it and make a point. So if you see the title up here, this graph designed by Dr. Fasel, who did the programming, is what the eclipse shadow looks like, not on the ground where we're at and observing it, but at a height of 300 kilometers. And if you think about that, it makes a lot of sense to know where the eclipse is affecting our Earth at 300 kilometers above the ground, because that's where it's impinging on the ionosphere, and that's what we're trying to study. So that's why this graphic, that this ground path may seem kind of large, but again, it's about 300 feet above our heads. Let's move on to the next one. Let's see. Oh, sorry, a second. May have got one ahead of myself. So April 8th, the path is going to be slightly different. Where it's starting in the Texas region right now. And as you all know, it's going over a lot of your heads and off New Brunswick and Nova Scotia and whatnot. So that's what we'll be studying this time around. So there's a couple of different things we want to talk about, and one of the reasons we're interested in eclipse studies and the ionosphere and whatnot, and one of the things we hope to do with the data we collect based on the QSO parties and whatnot, is to see an improvement in the models of the ionosphere. I'll take a minute and kind of make an analogy between terrestrial weather, which we all experience as rain, snow, sleet, and occasionally sunshine, and space weather. The local meteorological weather forecasts have improved greatly in the last 30 years. They're not perfect by any means, but they've improved greatly. That's because computing power has increased. The mathematical models that were created have been improved. They've collected a lot of data. People with backyard weather stations sending in data of wind speed, temperature, precipitation, humidity, so on and so forth. And the people that develop those models use that data to improve the models and make them more accurate. The same thing is true of space weather. I'm going to show a little graphic here of of a prediction on how the ionosphere should be reacting during the eclipse. Now, what this is a measure of is at least to me, it's always been a kind of an obscure term called total electron content. If you just think about it, that's a measure of how many free electrons are floating around way up there in the ionosphere. Now, the color scale here, when you see this happen, it's basically from the total electron content. If it's blue, it's dropping. If it were in the red, that means it's increasing. So let's take a look at this thing and see how this guy runs for me. Whoop. This, of course, is from last October. I'll run this at least twice. So what you're seeing there is this big blue region represents a lowering of the total electron content. That's because the moon was between the sun and the earth, and the sun's UV radiation was no longer able to shine on the ionosphere. So the electrons in the ionosphere, instead of being as energetic and moving around, they started to recombine, and the atmosphere became more neutral. So where the total electron content was going down. Let me see if I can continue this. I'll stop it once more.
Very fast question. That
Yes.
decrease represents what fraction of the daytime ionization?
That's an excellent question, and it's unfortunately above my head or outside my pay grade. That's a great question, but I unfortunately don't know the answer.
No problem. No problem. Thank you.
Okay. Yep. Let me restart this. What I'm looking for are these little bubbles over here on the right that are going to form up on the right. See these guys here? These models, you know, sometimes you could say, okay, yeah, I understand that the electron content's going to drop down as the eclipse moved across this part of the world. But you may say, what are these little barbells? What do these little guys mean? And there's a lot of interesting stuff going on in the Earth that's really not obvious to most of us. It turns out there's an area along the equator called the equatorial anomaly, and there's an effect called the fountain effect, where the interaction between the Earth's magnetic field, electric field, and gravity cause the electrons to move in a pattern that you may not expect, but they certainly do happen. And what I want to do is jump into a visualization from NASA here. Let me see if I can jump over to this guy. Let me see this. Whoop, that's not working. Let's try this again. Okay, are you guys seeing a picture of the Earth? I hope that national visualization. So this is a demonstration of what's called the fountain effect. When you see the electrons are going up as they would in a fountain and then falling back down. So I don't know, I can't tell you exactly how that type of interaction, how that affects the ionosphere, how it affects HF radio propagation. But if you know, we all know that the PJ2Ts of the world and some of the other stations located along the equator, remember HC8N, you've got who else, D44BC and so on like that. They have put out some pretty good signals, and it's possible that some of these effects are due to their location near the equator. And if we have more data, we can start to understand how some of these things work and how they affect HF propagation. Okay, here's one more demonstration of another tool, another modeling tool that's used. This is a tool called FARLAP, and it does what's called ray tracing. Signals emanate from our antennas. They're refracted by the ionosphere and back down to Earth. This was from a 2017 during that eclipse modeling. But you can see in the bottom how the signals, the red is kind of the average of the signal path. And these are, again, these are some of the tools. So, you know, what I'm saying is these tools today are not necessarily available to us as radio amateurs. They're probably very difficult to run and use very large computers and so on and so forth. But it'd be great if through HamSCI's efforts and the efforts of other researchers, we could someday have access to these tools if they were accurate. I mean, think about getting on, working out a day or two before the contest, knowing what the solar flux prediction is and so on and so forth. And using tools like this, those of you who have stacks of tri-banders can decide, do I need to use the tall one? Do I need to use the lower one, depending on angles of radiation and so forth? So it's, I think there's a lot of potential for these tools to help us as amateurs, and that's why we're hoping that we'll jump in and contribute a little bit to the study of these tools. So let's get back to the eclipse. So, you know, what questions do we have, or what questions are the scientists asking about the eclipse? You know, the first and foremost is, can the solar eclipse be observed in HF communications? And I've got some examples of that. How large is the disturbance? How long, you know, with the eclipse, if you're in the path of totality, it's only a few minutes over your heads. But how long before the eclipse actually goes overhead do we notice the effects? And how long after the eclipse goes by do we still notice effects, changes in propagation? Symmetry. You know, I'll show you some pictures that show that, you know, maybe an hour before the eclipse, we started seeing things, but in a half hour, those eclipse effects start to fade away. There's an asymmetry there, and we're trying to understand that is. And of course, just general questions on propagation. And as I mentioned earlier, gray line, how similar is an eclipse to gray line? You know, gray line happens over many hours typically, where an eclipse goes by, the moon's actually moving at supersonic speeds. As we can really kind of speed things up as we're observing. So what we've done, we've accumulated all of our little projects and programs and contests under a cute little name called the HamSCI Festivals of Eclipse Ionospheric Science. So here's where I transition from talking about astrophysics into amateur radio a little bit. So at last count, we at HamSCI are sponsoring 7 different events, asking people to get on the air, make QSOs, get spotted, create data, and even some of our antenna or some of our experiments are involve more receiving than transmitting. So there's kind of something there for everybody. And I'll go into what some of those events are right now. So the festival, here are the 7 events, and I'll talk about the first 5 in detail. And let's see. So the first one, the most obvious, is our Solar Eclipse QSO party. Real simple. It's kind of like the North American QSO party, just held during an eclipse. You know, it is definitely a contest. N1MM's got a template for it. It was just updated in the last couple of weeks, thanks to the developers. CW and digital contacts are the most valuable. FT8, which some people like and some people don't, is actually a very valuable mode for us because of the fact that most people's FT8s is they receive reports on their screens. If they send them off the PSK reporter and some of the aggregation sites, that provides a very rich set of data for us to use afterwards. But the rules are on the HamSCI website. I don't need to go in with you guys because they're all pretty straightforward. But the key for us is that these things generate some huge data sources, and the numbers are actually pretty impressive. So we've done this twice before. 2017 was very successful. We're working on the scoring for October, but we've got some preliminary information. And then of course in April. Now what you'll notice looking at the times, we start the QSO party about 3 hours before the eclipse comes into the US mainland and lasts for about 3 hours after. So we get plenty of data kind of before, during, and after the eclipse. That makes the best science. But what we really end up analyzing, and this is from 2017, is the number of spots that come through. You know, I mean, some people, CW skimmers and the digital modes and whatnot, develop a huge amount of data. And that data is stored, it's accessible to researchers, it's accessible to any of you if you want to go through and look through it. But just as an example, in 2017, you could see if you total this thing up here, we've got over 2 million spots. When you talk about spots, you think about it, we know who the transmitting station was and where they're located, their grid square. We know the receiving station based on their grid square. We know the time of the QSO, and we know the frequency that QSO happened on, essentially which band. So that's basically, that QSO, it represents a chunk of data. And if you multiply that by 2 million, that's a lot of interesting stuff to analyze. And you know, even one QSO though can be received by multiple skimmers or multiple FT8 operators if you want to use that mode. And that gives us a lot more data points because again, we know where the transmitting station's at, but there could be multiple receiving stations, and every one of those guys makes a new data point. So these are the three primary sources of data we used after 2017 to come up with some of the results I'm going to show you. So here we are about 6 years later, and I think we're going to get tremendously large more data this time around. Again, and respecting a lot of credit to the FT8 operators because there's so many of those guys on making so many contacts and reporting their information. Now, when the researchers take this data in and start working on it, they don't just rely on the ham radio data alone. Typically, scientists will look at multiple data sets, look for correlations and similarities between them, and there certainly are other data sets like the global positioning system. There are ways to measure this total electron content. There are other radar systems that are bottom side sensing of the ionosphere, the super darn network, ionosounds and other things. So the amateur radio data is very, very important. We do kind of correlate it and check it against other systems. So this is just a graphic in 2017 of basically the observations that were made. The blue stars were the receiving stations, and the red dots and stuff are the transmitters. So this just gives you a picture, as you probably expect. Most signals were transmitted from the Midwest and along the East Coast. Things thinned out on the West Coast a little bit. But the point here is we had a lot of data, and this gives a nice graphic visualization of how much information was out there that we had to work with. So okay, so what did come of this? So in 2017, Dr. Purcell did this analysis and has published a number of peer-reviewed papers on what happened. And what I'd like to do is to go over this top diagram in detail because I think you'll find it interesting. So what we have here are observations of signals of QSOs, as I said, transmitter, receiver, frequency, and time. And this particular set of data was just focused on 20 meters. The vertical axis is distance. How long was the QSO? What was the endpoints between the transmitter and the receiver? And the horizontal axis is time relative to full eclipse obscuration. Now, this is assuming the center of the United States, probably a spot in Kansas. You got to start with some point, right? But so at the 00 time, that means when the eclipse was directly overhead in Kansas, half hour before, an hour before, and the same thing, 30 minutes, an hour, hour and a half after. The colors, this is known as a heat map. The colors are important because they give us some information to spot density. Darker the colors, the reddish colors, more spots. So what we're seeing here, about an hour and a half before the eclipse passed overhead, there were a lot of QSOs being made at a range of 1,000 to 2,000 kilometers. And that condition remained for another half an hour until about an hour before the eclipse. But notice the colors start to change at this point. As the moon is blocking the sunlight, as the ionosphere is changing, we're seeing fewer and fewer QSOs, the lighter and lighter colors, between 1,000 and 2,000 kilometers. In fact, as we get to within about a half hour of the eclipse, you can see the spot density now is much, much lower. There's about half as many QSOs being spotted. And right when the eclipse was overhead, we're into some very low spot densities. So 20 meters didn't close down entirely, And remember, this was also during the low point of the solar cycle, but when the eclipse was overhead, 20 meters is pretty well closed down. But within about a half hour after the eclipse, it started to wake back up again. You see the spot density now we're into yellow. Spot density is going up, up, up. And then it increased from an hour out, maybe to an hour and a half. But the interesting thing here is I talked about asymmetry before. Notice what the band looked like before the eclipse and what it looked like after the eclipse looked to be different. We don't quite understand why that is, and that's another thing we'd like to figure out. Now, some other comments I made earlier too is we want to verify what some of these numerical and computational models are all about. So this was a prediction of what the spots would look like based on a model called SAMI-3, and using some of that ray tracing technology I showed you earlier. And this was SAMI's 3 prediction for 20 meters, and before the eclipse and after. And if you look at the upper and lower diagrams, they're not exactly the same, but they tell you that the model wasn't too far off. It wasn't too bad. So what the hope is that this time around, we've fed some of that amateur radio data into the new model. They've improved it. And we're hoping that in October of last year, in April of this year, we see that the model more closely matches the actual observations. So this is a little bit busier, but we were talking about top band and 160 meters earlier, right? Well, this is pretty much, let's look at this last one here, which you pretty much expect in August of 2017. You've got no spots. I mean, who's going to be on 160 and what's going to propagate at that time of day, right? Well, look what happened right about when the eclipse was overhead. All of a sudden, there's kind of a bloom here. You definitely see some spots, some traffic on 160 meters right at the darkest part of the eclipse. And it didn't take long, maybe 15 to 20 minutes, when the moon had moved by, when the ionosphere was illuminated again, when 160 again closed down. And the model kind of sort of predicted that. I think the 40-meter graph is interesting as well, because 40 meters is running about 500 or so kilometer paths. And when it got dark, when the moon was blocking the sun, look what happened. 40 meters got longer. About the same number of QSOs are being recorded per minute, but their distance increased. Not a surprise when it gets a little bit darker. So there's your kind of your gray line effect. And then once the eclipse went by, 40 meters shortened back up again. So what we take away from these graphs is we think that using amateur radio data is really a valuable and valid way to study the ionosphere and see what's going on. Notice on the right too is that the SAMI-3 models were again reasonably close. They had about the right shape, about the right distances, some room for improvement, but they were pretty good. So let me talk about a little bit different type of a contest, a little event. I mean, some of you may be familiar with WSPR Whisper. That's a propagation study mode. And there are a lot of people who like to transmit whisper signals on 7040, and there's frequencies on all the other bands. And there's whisper receiving stations who receive them, record their signal strengths, and then again, upload them to a database. The most popular database is called PSK Reporter. It was started by a guy up in Massachusetts, Philip Gladstone. And we ended up naming this particular contest after him. And this is an event where people who operate Whisper can enter, and we basically count who's got the most spots and who contributed the most data. And that's kind of sort of what that event is all about. Of course, all the rules and stuff are on the HamSCI website, very easy to get to. The next thing is a little bit different. It's not just about operating, it is about receiving, but it does provide some interesting insight to the ionosphere. This is called our GRAPE HF Doppler experiment. What happened is the folks at Case Western Reserve University had an idea and developed this little receiver on the right. It's a little board. It's less than 1 by 2 inches. And what it does, it receives a single frequency. Typically, like at my house, it receives WWD on 10 megahertz. It's a surface mount board. Order the parts from DigiKey or Mouser or somebody like that. Put it together yourself, and build up a system. So it's a way to do kind of hands-on citizen science instead of just buying something off the shelf. A lot of us like to build things, right? And this is just another case of that. We actually have grants. We're funded by the National Science Foundation, NASA, and some other organizations. And there was a group of guys in New England and Massachusetts who built a number of these great systems, and then we deployed them around the country to specific places before the last eclipse so that we could collect data. So this is part of our mission to develop interesting hardware and get it out into the field. This is the group of guys that was putting everything together and doing all the programming and stuff. And then I helped figure out where these things had to go and worked with the recipients and some of the logistics and that sort of thing. But it's a great group of volunteers and a great opportunity to contribute something to science through amateur radio. So what is all this grape and this Doppler shift stuff about? Well, if you think about how HF propagation works, and we'll use WWV as an example, they're transmitting on 10.000. They're accurate out to something like 10 to the 13th decimal places. The signal goes up, is refracted off the ionosphere, and comes back down to a receiving station. The key to think about here is that the ionosphere is not static. It moves. It moves from day to night. It moves due to CMEs and solar flares, radiation storms. There's things called acoustic gravity waves that can affect it. But so the ionosphere, this refraction point, is always moving up and down, very rarely static. And if you're familiar with the Doppler shift, if you think about if you're standing on a sidewalk, you're listening to an ambulance coming at you with their siren. As that ambulance approaches you, what happens to the frequency, the pitch, it goes up because the audio waves are getting compressed. They're becoming higher in frequency. When the ambulance goes past you, you hear the pitch of that siren go down. Again, that's a Doppler shift, excuse me, because the waves are actually getting stretched out. The exact same thing happens to RF. As the ionosphere moves up, the path length increases, so the apparent received frequency decreases. And that little receiver I showed you earlier is able to resolve the received frequency to a couple of tenths of a hertz. And I'll show you some graphs about that and how all this stuff works. So this is just a really cool experiment that's used to basically sense the motion of the ionosphere. So this is an example of a graph from one of these grape receivers here at my house in Cleveland. This is fairly typical. The red represents signal strength. The black represents Doppler shift in frequency, and you can see the scale on the left for Doppler shift. It goes between plus or minus 1 hertz. So again, these things are really accurate. Their frequency is controlled by a GPS disciplined oscillator. And this graph here is a fairly typical day. Most days without any kind of big solar perturbations look like this. And so notice that band there, what I've got there in the blue between about 15 and 1800 Zulu, pretty quiet, not a big deal. This was the day before the eclipse. The day of the eclipse, things look quite a bit different. You see the drop in received frequency. That implies that the ionosphere was moving up. And then after the eclipse went by, that black line goes up and burbles, and then it kind of comes back down and settles out about 1800 UTC. That's after the eclipse has gone by. So this is something we kind of expected to see, and we were glad to see that our expectations were met during the eclipse. These effects here are very similar to dawn. If you back up a couple hours, you look at between about 12 and 1300 UTC. You see a lot of big spikes there in the black line. That's something that happens at dawn every day. So that's kind of the gray line effect we see every day. And in between the blue bands is kind of the eclipse-induced gray line. Now, so you don't think that was just my receiver, maybe my neighbor turned on a vacuum cleaner or something like that. This is a layover of a lot of the stations who have these grape receivers, and you can see during that same eclipse period, they all saw the same effects. So we see that this drop and this increase are pretty consistent across not only the grape equipment, but across the country as well. Now we've got a number of different types of equipment and softwares running. We're always trying to find out better ways to graph and analyze this stuff. And this is a slightly different data format called DRF, the digital radio format, which was developed by the folks at MIT. And again, you can see here during a typical day on dawn, you get these dawn effects, you get these funny looking peaks. And during the eclipse, we see a similar shape. Not exactly the same by any means, but similar. And I think if the mathematicians work on these graphs a little bit, we can extract a lot more data than we're just seeing visually. But this is, again, a different way and a different way of looking at the same gray line phenomena. All the data we collect goes to a central server at the University of Alabama. And this is our map of the grapes. I think it was on Eclipse Day. So we've got a number of contesters on this map. We've got N2IC in New Mexico. We've got K5TR, George Freeman is there in California, and a lot of other interested observers. So we've got some good people. Yeah, Ward Silver's on here too, N0AX. So we've definitely got some help from the contest community. The last thing I wanted to talk about in detail too. A couple of fairly new things that just cropped up. We talked about the whisper mode earlier. There's a group of people in California and the UK and across between the two that have developed some software called Whisper Demon. It uses a slightly different code than standard Whisper, but it allows us to pull a lot more data out. And these are some what we call noise plots during the eclipse period. So again, you can see the same kind of shapes, the same kind of phenomena between about 1500 and 1800. It's just a different way of looking at what's going on for the eclipse. So again, it's the more different ways scientists have to look at the data, the happier they generally are. Another interesting one that we've got a few people participating in is something called a time difference of arrival experiment. And I'll go over this one real quickly. We basically have pairs of stations that transmit some audio tones. Excuse me. And these two stations were on the western U.S. And when you think about HF propagation, many times we get a single hop between two locations. You'll see here the ground distance of about 317 kilometers. And that takes a finite amount of time for the signal to travel from the transmitter to the receiver. But sometimes you get multi-hop propagation. So it takes a little bit longer for the signal to get from the transmitter to the receiver. And sometimes you get both simultaneously. What Steve Serwin and his compatriots have figured out is that if you transmit some very specific, very clean, clear audio tones between two locations, you can actually figure out the difference of time of arrival between those signals based on one hop versus two. And Steve has worked out the mathematics to calculate actually the height of the bottom side of the ionosphere. So this stuff is a little more technically detailed, but it just shows you some of the interesting things that volunteers with HamSCI are doing to better understand the ionosphere. In fact, if you listen to WWV at 8 minutes past the hour, you'll hear these special tones that are being transmitted. We originally used the WWV station to characterize some of these tones, and we're quite successful with it. So this particular event, kind of like a contest, lasted about 8 hours. So Steve and the other station transmitted pairs of these tones back and forth every 15 minutes. And there's a lot of graphing and a lot of mathematics and stuff that still has to happen. In fact, there's one of the classes, Dr. Frisell's classes at the University of Scranton is going through and doing the analysis right now. So probably enough about our projects. If this kind of thing interests you, number one, we'd love to have you operate in a Solar Eclipse QSO party. It's on a Monday. No other contest going on that day. Well, I guess the medium speed tests are going on too. But get on, operate, take a look at our pages on the web. If you're interested in joining doesn't basically just mean signing up for our Google group, and you can see what we're going on. And we've got a number of different teleconferences and Zoom calls and stuff during the week as well. Of quick plug at my alma mater, HamSCI has an annual workshop where a lot of these ideas are presented, papers, poster sessions, and so on and so forth. A lot of collaboration occurs. We invite students even from high school through college to come and learn and be part of it. And we typically give exams, there's VEs there and that sort of thing. So it's a big, it's just a good time. It's coming up in next month. I do want to acknowledge, as I said earlier, HamSCI doesn't have a revenue stream. We are funded by the National Science Foundation and NASA, so I guess I need to thank the U.S. taxpayer for help us. ARDC, Phil Karn and his group also fund some of our projects. And of course, there's some universities that support us as well. So we're very grateful for all of that. So to those who participated or thinking about participating, if you're at the Orlando Hamcation, stop by and see us next week. We'll have a booth in one of the halls. That's about it from Cleveland for now. Questions?
Yeah, excellent. Thank you, Gary.
I have a question, if you don't mind, please.
Yes.
Yeah, you mentioned a great deal about HF propagation, but what about VHF? Is this affected?
Most of the research, in fact, all of the research right now has been on 6 meters and below. And we don't have nearly enough stations participating even on 6 meters to come to any conclusions about VHF. So I guess that's, as we used to say in college, that's an exercise that's left to the student. Hopefully in the future we can consider doing some more with VHF.
Thank you very much. Or I'm sorry, once again, can I participate in somehow for a VHF or 6 meters data for you? Can I do that?
If you could put up a 6 meter whisper beacon would be the best thing, because so the other whisper stations can pick you up. That's fairly straightforward. There's a lot of activity on 6 meter FT8. And if that data is then transferred to PSK Reporter, that would help us as well.
Okay, very good.
Translated as get on the air.
Yeah.
Thanks very much.
You're welcome.
This is
This is
Jim
good.
K1IR.
Go ahead, Jim.
I apologize. I had to be in and out of your presentation. I love the presentation. I had a question. I'm not sure if you might have answered it while I had to be out. Who are the primary consumers of your research other than the amateur radio community, and what kinds of practical applications might it affect?
From a science point of view, most of this research is presented at conferences like the American Geophysical Union. We work with NOAA, NCAR, the National Center for Atmospheric Research. And I think right now it's more of a pure science thing. But if you think about the ionosphere, whether you're Elon Musk and you've got your Starlink satellites, or you're NASA or the military, your signals are passing through the ionosphere. So the idea of an organization like HamSCI is to do good science, do research, have peer-reviewed and publish your papers. You don't really know who's using your published papers and data. So I guess I'd say that we don't really know, and it's more pure science than applied science at this point.
Thank you. It's all very interesting regardless.
Hey, this is Rudy on 2WQ. I also have a question related to the application of this research. It's fantastic and obviously supported by tons of data. I'm wondering if there is an immediate application to feed it into vocap and other real-time propagation models, prediction propagation models, so that all that research doesn't go in vain and doesn't go just in research papers.
That's a good point, and that's kind of my hope too, and that's one of the reasons I enjoy participating. My guess is, and again, I'm not the scientist here, but my guess is that vocap uses things like what's called the IRI, the International Reference Ionosphere, as it's doing its calculations. And today I showed you some examples of SAMI3, which is just a different numerical or numeric model of the ionosphere. My hope is the folks that write vocap and stuff will use these improved models and to make better predictions. That's the hope.
That would be awesome. Thank you, Gary.
So I have a question about Whisper. I'm not that familiar with the mode, but I understand I could potentially kick off like a beacon, I guess, and have it running at my home station while I'm up in Vermont doing the contest. Is there such a thing as too much data? I guess if you had too many Whisper beacons going.
I've never heard the science folks complain about too much data because every station is different. Every antenna is different. And occasions, how it is, stations go off the air, things happen. So I think more data, I think, is always better from their perspective.
Okay, I'll look into that. Excellent. Any other questions? Gary, that was excellent. I really enjoyed that. Thank you and your team for supporting that. This came together pretty quick. They had reached out to K1ZZ, who then forwarded it on to me, and within days I had a second talk for a meeting this weekend. Again, thank you for your time. I'll be in touch with you as we go forward. With that, you're welcome to stick around. We got like one more thing to cover, but otherwise, thank you so much again.
All right, good. One last point I'd like to make real quickly is what we're putting out, what you're going to start to see in the amateur press and stuff like are some of our observations from the recent eclipses. That the actual science project or science process of peer review and publishing and stuff to where we can actually have specific findings, unfortunately takes years. That's what I'm learning. So you're going to see some of our observations to get some idea of what as I've gone over today, but the actual results, whether it's, assisting with making a better version of vocab or something else, unfortunately typically takes years. So appreciate everyone's patience. Thanks for your time today and hope to work some of you in a sprint tonight.
Oh, okay.
Hey, Gary, I'd like to say thank you to you also for a very interesting presentation. This is Chet, N8RA, and I was also glad to see the W8EDU is still around because myself and Dr. Marshall Crouch got that radio club started again when I was a student back there at Case in the early 60s.
Wow.
Yeah, it's very active. They've licensed a lot of students. It's actually part of the curriculum. And Chet, I do remember you were back in the Cleveland in the late 70s when I first got licensed. I do recognize your call. So,
well, there's no place to hide, I guess. Thank you.
Nice.